So our today's topic is root locus analysis. So let us start with this. Probably I'm looking for where I have kept my slides. Okay. So let us start. Yeah, got it. So root locus is a time domain approach, and it was the who was the pioneer behind it? Walter Evans. Okay, he has developed this method. Basically, he was a mathematician, and we have in any expression in the form of transfer function, we have poles and zeros. Okay, so he has taken by making denominator equal to 0, we get poles, and by making numerator equal to 0, we get zeros. So he has just plotted these poles and zeros, and on the basis of this, he said many things can be commented, even the stability also. So basically, it is a graphical approach. Okay, so you have to keep in mind that that this is an graphical approach. Okay, and this graphical approach have certain steps. Okay, and this is being plotted on ordinary graph paper. So dear students, before starting the problem, solving the problem of any root locus, you should have an ordinary graph paper, that is green color graph paper, available in the market. That should be with you. Okay, and pencil, rubber, scale, and everything should be, instrument should be with you. Okay, so just as we in our lower classes or even in our first year level and second year level, you used to plot graph on a graph paper, ordinary graph paper. Here also we will plot the graph, and that plot will be called as a root locus. Okay, so let us first of all understand what are poles and what are zeros. Okay, and that is, I think so, you know it because you have learned so many things. So zeros are clear. If a transfer function is of the form k s minus z1 s minus z2 up to zm. Okay, similarly there is an expression in the denominator s minus p1 s minus p2 up to s minus pn, then z1 z2 zm are called zeros, and p1 p2 pn are called poles, by equating the numerator and denominator respectively to zeros. And we can plot in a s plane. The s plane consists of two axes, the real axis and the imaginary axis, and the pole are being represented by cross and the zeros are represented by circle, as shown in the figure. So it is very clear that how to plot the poles and zeros of any given transfer function. And also we know that for our second order closed loop transfer function, okay, the response yt is given by this, and if you will find out its poles and zeros, there are no zeros are there are only poles are there, and these poles are nothing but s1 and s2, two poles are there which are in complex conjugate form, and their value is minus eta omega n plus minus j omega n 1 minus eta square. So both has been plotted here. So these are the roots of the characteristic equation of a closed loop transfer function of second order. So these have been plotted. Okay, and with the help of this equation, you have find out many things like damping ratio, peak time, settling time, and the maximum peak overshoot. This we have already done in the time domain analysis. Now we will able to find out the same things with the help of this root locus also. So generally a confusion is there. In the Viva was also it has been asked, root locus is a time domain or a frequency domain approach. So by graph, because being a graphical approach, so it seems among the students that it is the frequency domain approach. But mind it, it is not a frequency domain approach. It is a time domain approach. Okay, so let us find out what are the other things related to it. Okay, and that we have already learned it. Okay, that if the poles like move towards the imaginary axis, okay, either positive or towards the negative, then we will find that the theta 1 will be less than theta 2. This will be theta 1, this will be theta 2, this will be theta 2, and thereby the damping ratio being cosine of theta will be theta 1 will be greater than theta 2 and theta 2 will be greater than theta 3, and similarly the peak time will be greater than peak time 2 and peak time 2 will be greater than peak time 3. So this is also an objective type question is being put forward before you, that how the set peak time and the damping ratio changes as the pole shift towards the upward portion of the imaginary axis. Okay, so similarly, if it is moving horizontally, okay, like P1, P2, in this case, the situation is just a reverse. Okay, reverse in the sense that in that case, if here this is the theta 1. Now you will ask the theta 1, this is your theta 2 and this is your theta 3. So theta 1 is greater, theta 2 is less, and theta 3 is again very less. So from that we will find a damping ratio theta 1 will be least, while eta 3 will be greater. Okay, and similarly can be commented on the peak time and on the settling time also. So just on the basis of poles and zeros, how to comment on the stability, and that we have already done it, that as I vary the damping ratio from 0 to 1 and then again moving on this side -1, what will be the response of the system? If eta is equal to 0, that is damping ratio is 0, then it is called undamped system, that is sustained oscillations are there, while if it is less than 0, it is called negatively damped, and if it is between 0 to 1, it is called underdamped. If eta is equal to 1, it is called and critically damped, and if eta is greater than 1, it is called overdamped. So and if you plot these all these roots, then you will find that they lie on a circle. Okay, that we can put mathematically also and graphically also as shown in the figure. Now come the concept of the root locus. Okay, so we have this type of system in general. Okay, a constant k is there, a forward transfer function gs is there, and a feedback transfer function hs is there. Now if I will find out its closed loop transfer function ys over rs, okay, then what you will find that when you solve it, it will come out to be kgs upon 1 plus kgs hs. If I will equate the denominator expression to 0, I will get characteristic equation, and when I will solve this characteristic equation, I will get roots, and these roots are known as the poles, and that is being known to you right from the beginning of the class. Okay, now what happens that I make a slight mathematical manipulation. I am shifting 1 towards that side. So what I will get, k GSHS is equal to -1, k GSHS is equal to, if I take the magnitude, then it will come out to be 1, and if I take, so what inference is getting from this, that the magnitude of this value is 1 and the angle is nothing but being -1, therefore it will be 2n plus 1 pi. So you have to mind it keep into account that what this k GSHS is there. First of all, this k GSHS is nothing but open loop transfer function. I have already told you in the chapter of the error analysis that GSHS, now some gain is being multiplied with, no problem. In fact, product of GS and HS is nothing but open loop transfer function, and with the help of this we use to determine the type of the system. So again I am reiterating the things. So k GSHS is equal to magnitude of k GSHS is equal to 1, and the angles comes out to be 2n plus 1 pi. This you have to keep in the mind, and these properties will be useful in solving the root locus. So using open loop transfer function for system parameters, we can analyze the closed loop system response as k is tending from 0 to infinity. So from these two equations, okay, we can now vary the k. Suppose k is the gain of the system. If I vary the k from 0 to infinity, what will be the location of the roots? Okay, how roots will be located in the S plane. Okay, and that plot is called the root locus, because it is the locus of the roots. Locus of the roots, there are so many points are there of when a particular parameter is being varied, and you are plotting these points. Okay, so you are getting a graph, and that graph we called as a root locus. That graph you called it to be a root locus. Okay, now after understanding that root locus is nothing and locus of the roots obtained by varying the gain k from 0 to infinity. In fact, the general definition is by varying from minus infinity to plus infinity passing through 0. But in general, in our undergraduate level, we generally vary from 0 to infinity, and we call whatever the graphs we obtain by varying the gain k from 0 to infinity, we called it as an root locus. Now, before proceeding to the plotting, because to plot the root locus, we have to remember 10 rules, 10 or 11 rules are there. Okay, that rules should be known to you by heart. Okay, and you require a normal graph paper, and you apply to any open loop transfer function, you will get the root locus, and then you have to comment on the root locus. So the first property, okay, now these properties are the rules only. First, so you have to remember by heart. The first property is that the locus segments are symmetrical about real axis. Okay, so they are symmetrical about real axis. Okay, symmetrical about R means there is a mirror image is there. Whatever is there in the positive side, the same is on the negative side. Okay, in order to explain this, suppose this is my graph paper is there. Okay, this is my S plane is there. Suppose I get a root like this, root locus on the I get like this, then a similar root locus will be exist or this. So it is symmetrical about real axis, not about imaginary axis. Mind it, this is the real axis. Okay, so the root locus will always, you will find, will be symmetrical about real axis. This is the first property you have to remember. Okay, and the second property, that is, the second property is that k is equal to 0. Okay, if k is equal to 0, then GSHS implies whatever the GS implies is the poles. And if k tends to infinity, okay, then GSHS implies zeros. Okay, so this property you have to also keep into mind. Now, the third thing is that how to find out the angle. Okay, how to find out the angle. Suppose there are three poles are there, 1, 2, 3. Three poles are there. Okay, and I choose the point angle SO. Okay, so what I will, and there is a 1, 0 is also there. Mind it, in this third I have three poles are being plotted and 0 is there. Now I want to know the how much angle is being there of this another point S naught. Okay, so what I will do, I will draw angle joining this point to the poles and the zeros, and now this is making theta 1, this is making, this pole is making theta 2, this is making theta 3, and this is making theta 4. So the angle contribution by zeros will be always be a positive, while the angle contribution by the angle contribution by the poles will be negative. So however they will get summed up. So angle contribution by zeros is theta 1, and angle contribution by the poles are theta 2 plus theta 3 plus theta 4. So net angle is theta 1 minus sum of theta 2 plus theta 3 plus theta 4. So you have to remember this, that to find out the angle of any point on the root locus, you have to adopt this procedure. Okay, now comes after going through this property, let us come to the step for construction of root locus. Okay, so you have a open loop transfer function. Mind it, root locus is always drawn for the open loop transfer function, though it system is closed loop, but we have to find out GSHS. So keep in mind that root locus is always drawn for GS multiplied by HS. Okay, so if in the question GS is given and HS is given, multiply, do this, and then start plotting the root locus. But if in the question 1 plus, if closed loop transfer function is there, then find out first of all GSHS. Okay, then only you will able to draw the root locus. The first step is that number of root loci is n or m, whichever is higher. Okay, so how many root loci will be there? That can be determined with the help of the degree of numerator or the numerator, whichever is higher. Suppose degree of numerator is 3 and degree of denominator is 4. So 4 is higher. So number of root loci will be 4. So whichever is higher will give you the indication that how many root loci will be there. So it can be an objective type question. The number of root loci for a given transfer function is how much? 3 or 4. So definitely it will be the higher number will be the number of root loci. So you have to determine from the open loop transfer function Open loop transfer function. Mind it that whichever is higher, numerator or denominator, and how much. Suppose it is the numerator is 5 and denominator is 6, then 6 is higher, so the number of root loci will be 6. Okay. Now root locus construction. First point is clear, number of root loci. Now each locus starts from poles and ends at zeros. Each locus starts from poles and ends at zeros. Okay, which means that suppose you have a graph paper is there with you. You have a graph paper with you. Okay, now in this graph paper I plot a pole and I plot a 0 also. Okay, let us suppose this is straight line. So the root locus will always start from the poles. So it will start from the poles and always ends in the zeros. Always ends in the. So for every root locus, the starting point is the pole and the ending point is 0. This you have to keep in the mind. Now suppose you say, I say the numerator or degree is 5. Okay, denominator degree is 6. Okay. So you will say how many root locus will be there? There will be 6 root loci will be there. Then you will ask, sir, if every root locus starts from the pole and terminates in zeros, then how this combination can happen? Yes, if this type of situation, definitely 6 root loci will be there and each loci will start from a pole and will terminate in zeros. But there are only 5 zeros are there. Then what about the 6th root locus? So what we will say that it will terminate in the infinity. That 6th locus will terminate in the infinity. It will extend to infinity. The same is true for the in case zeros are higher. If zeros are 6 and poles are 5, then definitely root locus will be 6. So we will say that this root locus is emerging from the infinity. So that should be clear. Okay, so if n minus m is greater than 0, then n minus m branches tends to infinity, and if n minus m is less than 0, then m minus m branch then infinity is towards the zeros. So you have to keep into this thing into mind. Now next come the root locus on the, now I have told you that how many root locus will be there. There will be some root locus that will be explicitly lies on the real axis. So how to determine this? So real axis segments or real axis root locus. Okay, they will be definitely symmetrical about real axis. I have already told you. And how to identify it? So to identify it on the real axis, the loci are to the left of an odd number of poles and zeros. So suppose there are this is say in this question, okay, 3 poles and 1 zero is being mentioned. So what you will do? You will do that now to determine whether on this real axis any root locus exists. So I will mark a point here. Okay, you need not have to mark point on your graph paper, but imagine that you have marked a point here. Now on its left hand side, okay, left hand side, on this side you count how many poles are lying, how many poles and zeros are there. So 1, 2, 3, 4. Okay, 4 are there. It is 4 is an even number. Hence, there can be no root loci up to from this point to this point. Okay, now let us take another point here. I take a point here. Okay, you need not have to draw. You have to just imagine in mind that suppose a point is there. Now on this left hand side, 1, 2, 3, 3 are there. It is an odd number. So definitely a root locus will exist here. Now again, you have to remember the property that root locus always start from the poles. So here there are in between this root locus, there are 2 poles are there. You mind there are 2 poles are there. Okay, so what will happen? This pole will start from here. This root locus will start from here. You have to mark the arrow sign. You have to make the line dark. The root locus will be made dark line, while all the other lines will be light with light pencil, while the root locus will be indicated by dark pencil. So I have just drawn the arrow. Okay, so these arrows are indicating that the root locus is starting from the poles as I already. Now let us take another point here. Okay, I mark a point here. So 1, 2, counting 2. Oh, it is an even. So there can be no root locus. Now I again put a here. Okay. Oh, there is a one pole is there. It is an odd number. Definitely a root locus will exist, and that is being shown by the red line. Okay. Now one more thing. Root locus starts from the pole and ends at the zero. So here, what will happen? I will show you by the arrow. You have to mark the arrow also. Okay. So it will start from this pole and it will terminate in this zero. So we have marked the two poles. We have marked the two root loci on this real axis segment, and mind it, all the other root locus will be symmetrical about this real axis. Okay, so it is very clear that you have to count the poles and zeros. If their odd number is there on the left hand side, then there is the existence of the root locus on the real axis. Now, after this, there comes the concept of centroid. Okay, so we have to find out now what happens. See, why this concept of centroid arises. Now, here the root locus is there. Okay, it is starting from poles. Now, you will ask, sir, where it terminates? Definitely, it will terminate at zero, but how it will move? It will terminate from here. So let us go by annotation. Okay, will it start from here? Or will it start from here? Will it start from here? From where, sir? Definitely this question will arise. And to give this answer, we find out another parameter called centroid of the asymptotes. Okay, the centroid of the asymptote is nothing but the summation of the value of the poles minus summation of the value of the zeros upon n minus m. So, for example, this is the open loop transfer function is there. Zero is how much? Value of 0 is 0, pole is -2, and another, when you solve this quadratic equation, -3 plus j3 -3 minus j3. Okay, now you sum all the poles. So -2, when you sum all these poles, okay, what you will get? It will come out to be -4. It will come out to be -4. So you have to locate a point -4 on the real axis. So here, suppose a -4 is lying here. Suppose -4 is like there. So your the other roots will be start diverging from here. Okay, so that will be clear, more clear in the coming section. So what I will do now, definitely you have pointed out the centroid point. Now, after pointing out the centroid, these root locus will be tangent or asymptotic to which lines? So we have to find out the asymptotic angles. Okay, and that asymptotic angles, these are all rules, mind it. You have to remember it. To find out the asymptotic angle, you have to go for this 2k plus 1 pi n minus 1, where k is from 0 to 1, 2, 3, n minus m, up to the number of the poles. Number of the poles. For example, how many GSHS is there? Okay, number of 2 plus 1 3. Sorry, there is something wrong is there. So number of the this is 0. This is m is equal to 3 3 1. So it is 3 and 1 is there. Okay, they have written a wrong thing. So okay, so here it is being written. So you can see that theta is come out to be 2k plus 1 pi upon 3 minus plus 1 is how much? 3, and 3, and there is 1 0 is there. So 3 minus 1, 180 degree upon 3 minus to 0 and 1 only. So when I substitute 0, it will come out to be pi upon 2 90 degree, and when I substitute 1, it will be 3 upon 2, 3 by 2 into 180 degree, it will come out to be 270 degree. Therefore, there will be two asymptotic angle with 90 degree and 270 degree. This you have to keep in mind. Now another example, suppose n is 6, m is 2. Okay, then it will be 180 degree upon 4, and you can easily find out these two angles. So you have to keep in mind that k will vary, start from 0, and it will vary from n minus m minus 1. Okay, so I should write down here that it will vary from n minus m minus 1. Okay, so the value of the k will start from 0 and vary up to n minus m minus 1. So you have to keep cautious about this. Okay, now there is a called breakaway and entry point, breakaway and break in points, okay, or entry points. Okay, so how to find out that breakaway? So what you will do, you will with the help of the open loop transfer function, you will form the character equation, that is 1 plus GSHS or 1 plus K GSHS. So once you have find out, okay, so and then once you have find out, equate it to 0, and then rearrange in the form that you obtain. The k will be on this term, that is the varying parameter, k will be on one side while all the other parameter on the other side. So you have to rearrange in the form of k. So once k is obtained, you differentiate it with respect to s. So you will get this, solve, equate it to 0, you will get certain points. Okay, now you have, these are points are nothing, either breakaway or break in points, which you have to plot on the root locus. Then come and another concept called angle of departure. So angle of departure and angle of approach. Okay, so angle of departure is nothing but 180 degree plus angle GSHS, and angle of arrival or approach. Some books written arrival or approach, that is 180 degree minus angle GSHS. For example, this is a closed loop transfer function is given, and you are being asked the angle of departure from the poles -1 comma minus j. So what you will do, that you will first of all, okay, you will find out the angle s plus 2. What is the angle of s plus 2? Minus angle s plus 1 plus j minus angle s plus 1 minus j. It should be equal to minus 180 degree, because it was as I already told you that angle GSHS is nothing but -1, so it should be minus 180 degree. And now angle s plus 2 is you can find out, but you have to find out the angle of the departure. Then what you will do, you will make it as a phi d, and then you can find out the angle of the other things. You will find it comes out to be 225 degree. So angle of departure is 180 degree plus angle of GSHS. Okay, so in this case it comes out to be 225 degree. Similarly, you can find out angle of approach at s is equal to z. So previously you have find out the angle of departure from -1 comma minus j. Okay, and now angle of departure is always from the 0. So say from the s is equal to j. Okay, so just substitute the value. Since s is equal to j is there, therefore I will make it as a phi a. Substitute all the values, you will get phi a is equal to minus 135 degree. Okay, so these are the two procedures to find out angle of departure and angle of. Then come the cross point of root loci imaginary axis. That for that purpose we will use the Routh stability criteria. Okay, so as I've already given you some numerical yesterday, where I have explained you that how to find out the marginal value of the k. So this marginal value of the k will be utilized here. So first of all, form the root array from the character equation like this. Okay, and then apply the condition that the root should be greater than 0 in order to the system to be stable. So from that, when I will place the limitly condition, I will come out to be k is 8.6, and I will also come to know that at what location. So once I get 8.16, I substitute it here, and when I will solve the so what will happen, that you just take and may form an equation just about that kth row, where the k is coming first time. So it is coming here. I will form an equation 20